Okay. Hi, my name is Sarah Fischel. I am doing my presentation, my seminar on the degree of the Brandt-Licorice-Millet-Hoe polynomial of the link, which is based on an article by Mark E. Kidwell. I have absolutely loved my time at Emporia. This is my last requirement before graduation. I got all of my classes done I started in the spring of 2015 and I finished in the fall of 2016. So I did it all in 6 semesters, and then I had a baby, my second baby, and put off doing the seminar. And now I am pregnant with my third, and I figured if I don't do it now, I'm never going to get it done. So here we are. A little overview of my seminar. I'm going to start by talking about knot theory, doing some basic introduction of it and definitions, the history of polynomials, and then we'll specifically talk about the Brandt-Licorice-Millet-Hoe polynomial, and then we will get into Kidwell's result that is the topic of his paper. I see I'm going to have to move some of this around to fit my head in there. Okay, so knot theory, introduction and definitions. Basically, we are thinking of a knot as a tangled string in Euclidean 3 space. So if you have some kind of tangled mess here, that's kind of the basic way to think about it. There's going to be some stipulations on it. For example, you almost have to think of it as being rubber. So if you have some kind of tangled thing, you could make it stretch out. That's allowed to happen, but you can also make it smaller, basically infinitely. Obviously, you still need to be able to see it, but it would be able to get as small or as big as you need. So you're allowed to stretch it however you need. A link is more often than not what this paper refers to a knot as. A link is technically the union of some mutually disjoint knots. So for example, I have a knot here, but actually they are 2 separate rubber bands. So these are links. So we could say this is a link, this is a link. And in our paper, we use that, or he uses that, rather than saying a knot. The projection of a knot is just the 2-dimensional picture of it. So if you see down on my screen, I have this rope that's kind of in this cute little knot, and the 2-dimensional picture of that is just a drawing of it that demonstrates or displays the crossings where the knot is crossing itself. So if I were to draw a basic projection of this, this rope goes behind itself, so I leave a space there. And then again, it goes behind itself, so I'm going to leave a space. And then it comes back through. Oops, I missed that space a little bit. And it comes through, and now it's going to go behind again. So we're just demonstrating where the crossings are. And I can't really see what happens there, but it looks like maybe it happens there, and then it goes behind itself again. So we can see where the over crossings are. So this would be a bit of a crude projection of this actual 3-dimensional knot. The isotopy in knot theory is distorting a knot without letting it pass through itself. So if we had a knot, you're not allowed to separate it as if it's made of several strands of string. So we're separating it, go this way maybe, and let it pass through itself. So I crochet, and sometimes this happens, like the yarn splits and you end up going through itself. In knot theory, that's not allowed. Okay, so we can't break that, cut it up, put a hole in it, and insert the string through it. We are, however, allowed to do Reidemeister moves. That preserves the isotopy, so we are not letting it pass through itself. And it will change the projection of the knot without changing the knot itself. There are 3 Reidemeister moves. The Reidemeister 1 takes just a single strand and basically, whoops, I wanted to use blue, and basically just adds a loop. Okay, so you can imagine that you could have a piece of string and easily add a loop that hasn't changed anything. Reidemeister 2, if you're looking at two strands, one strand remains the same and the other one you could always just push behind it. Okay, and you can see that that would not change the actual knot. And Reidemeister 3, so we have this one strand back here that's kind of behind these other two strands, and it's just going to push to the other side and go behind that way. Okay, so these are our three Reidemeister moves that are allowed to be used in order to change the projection of the knot without changing the isotopy. An invariant in knot theory is a quantity which does not change under isotopy and the Reidemeister moves. So we are allowed to do these Reidemeister moves and they will not change whatever invariant quantity we're talking about. So that basically means that any projection of the same knot is going to have that same invariant quantity. Invariants are one of the most successful ways to tell knots apart, and one of those invariants are polynomials, and that is what this paper talks about as one particular type of polynomial. Most of knot polynomials are Laurent polynomials, and that means they have positive and negative exponents. So most of our polynomials definition, basic definition, is that they can only have positive exponents, but a Laurent one can have negative as well. And then I wanted to give you a brief history of polynomials. I actually found this part extremely interesting. It's nice, you know, I'm used to teaching a lot of Algebra 1 at the high school level, and a lot of the stuff has been around forever and ever and ever, and we don't really get to deal with a whole lot of new recent discoveries. So while this might not seem super recent to my students, because they're like, hey, that's in the 20s and the 80s, we know as mathematicians that there is new math all the time, and the kids don't always see this. So I actually got to share a little bit about this with them, to teach them that, you know, there are all kinds of new things that can be discovered in the world of math. It's not an ancient language by any means, or a dead language, I mean. So anyway, in 1928, James Alexander discovered the first polynomial, which appropriately we call the Alexander polynomial, and this was the only polynomial for 56 years. Nobody really messed with it. It worked. It was good. In 1969, John Conway, he found a new way to calculate that same Alexander polynomial using what is called a Skene relation. A Skene relation relates the polynomial of a link to polynomials of links obtained by changing just one single crossing of the original link. And we'll see one of those here shortly. So we were still only working with the Alexander polynomial. We just now had, due to John Conway, had a new way to calculate it. Then in 1984, Vaughan Jones discovered a new polynomial. So this was the first new one discovered since then, only the second polynomial that we had in knot theory, appropriately named the Jones polynomial. And when he did this, this created kind of a new flurry of interest in polynomials. People, some mathematicians, they got excited and they realized that there was a lot more work to do in this particular area in knot theory. Mathematicians wanted to find a two-variable polynomial that would combine and generalize both the Jones and the Alexander polynomials. And very shortly after, several people were successful in doing just that. So just 4 months later, what came to be known as the Homfly polynomial was introduced. It is a two-variable Laurent polynomial. So again, two variables can have positive and negative exponents. It did generalize successfully the Alexander and Jones polynomials. So those actually then became special cases of the Homfly polynomial. Interestingly enough, 6 people working in 4 independent groups are credited with the discovery of this, and they are listed here. 2 of them were working individually, and then there were 2 groups of 2 as well. Very sad story. These 2 gentlemen also, and I'm not going to try to pronounce their names, they were from Poland, but unfortunately But unfortunately, due to the circumstances in their country, in Poland at the time, their results did not get out of the country and into the mail and into the hands of the math world until later. So they really don't get the credit that they probably deserve. I've seen a couple times it referred to as the PT HomeFly or the HomeFly PT, but that's super rare, and I would imagine nobody really calls it that. So it's really unfortunate for them, but the other 6 gentlemen, they received credit. And then I actually found this really neat picture of Jones with those 6 gentlemen. And then I totally went down a wormhole here doing research on them, and many of them are still math professors. Some of them have some scandal in their lives, which was where the wormhole led me. And I won't entertain you with that at this point, but it was really interesting to see kind of where they're at now, and to me they're like famous in the world of knot theory, and kind of cool to see that they're still teaching and you could just go and take a class from them at really typical basic colleges, some of them too. So anyway, little history. Okay, so that brings us to the particular polynomial we are talking about. You can see that some of these people are the same, Brandt, Licorice, Millet, Hoe. Going back to our HomeFly gentlemen, you can see that Licorice and Millet are in there. After I should have said this, so note to self, when I'm doing the presentation, I need to talk about how this led into other polynomials. So after the HomeFly polynomial was discovered, many more polynomials were discovered. A lot of them are very similar from what my research has shown me. They all seem to rely on a Skene relation and another rule, which we'll talk about in a second. But there were many more generated after this, and my article focuses on one. My article was published in 1987, so this was a lot of like mid to late 80s. There was a lot of these new polynomials coming out. The one I'm focusing on is the Brandt, Licorice, Millet, Hoe polynomial. It is a Laurent one variable polynomial. It is represented by Q of L, where L is an unoriented link. So some of our links or knots can be oriented, and what that means, let me just draw really basic. Not an oriented one just means that there's a direction given on it. Okay. For the HomeFly, that one is oriented, but for this particular polynomial, we do not have to have any orientation. So that is not necessary to describe which way you should be following the knot. It is defined by 2 rules, as many of the polynomials that I found in my research were. The first one is generally saying that the polynomial of the unlink is 1. My author chose to use a U for that. Oftentimes we see it as actually the unlink. What is the unlink? The unlink is just a circle. Okay, so it is not knotted with anything. It is a separate link, and there's no knot that could not be undone there. The unlink, also known as the unknot or the trivial knot. So the polynomial of it is 1. That's our first rule. The second rule is our Skene relation, and I will talk about that more on the next slide. So again, a Skene relation is looking at a projection of a knot and then changing it at exactly 1 crossing, so only in 1 place, and the polynomial will then relate those projections. So if we have a projection, we are saying this is our L positive link. Oh, Dr. Wiley, question. L positive, L plus, what's the common way to say that? And then L minus, L negative, L naught, L infinity. What should kind of the nomenclature be there? Okay, so just looking at our different projections here. So we have maybe some complicated or not complicated knot, some type of knot or link, and we are saying that a crossing that looks like this is our L plus. And if we take those and switch which one is on top, then that would be L minus. So we've now changed the projection of our naught, but only in that one particular crossing. L naught takes the crossing and eliminates it completely in this manner, kind of a horizontal manner. And then L infinity also eliminates the crossing, but it does it in this type of vertical manner. Okay, and this is all based off of your original length, and generally we let the original length equal L plus. So the Q polynomial, as we will refer to it, relates these four projections in this manner. Okay, so the Q polynomial of this plus the Q polynomial of this projection would be equal to x times the Q polynomial of this projection plus the Q polynomial of that projection. Now, one might notice that these two projections have exactly one less crossing than these two projections, and those two happen to be multiplied by x. So it might logically make sense, or intuitively make sense, that the degree of the Q polynomial has something to do with the number of crossings, since when we took a crossing away, we had to then multiply by x. However, that's not true, because this is the Q polynomial is an invariant, so we know it does not depend on the projection, and the crossing number does depend on the projection. It's not an invariant, so that can't be the case. But what we can determine is Kidwell's result, which proves that the degree of the Q polynomial is less than or equal to n minus k, and in a second we will talk about what n and k are. Some notation that Kidwell will use: the DEG of Q is the highest power of x in Q of x. So we're talking about the degree of our Q polynomial. P of L, or just P at times, is the projection of the length L, and N, or N of P of L, I reversed those there. N of P of L, or N, is the number of crossings in that particular projection. So there's our N that's coming in our theorem. Oops. B is a bridge, and a bridge is if you have any projection of P, if you could delete the undercrossing points of L and partition the rest of L into open segments and closed curves. These open segments and closed curves are the bridges. Dr. Wiley, at this point I want to have a prop that is, I'm thinking of making it out of clay, where I have like maybe like a circle of cardboard, and then on top of the cardboard I have bridges made out of clay, individual pieces, and then like maybe a separate open segment somewhere or a link, and then like the bottom of it as well, but to show that this is how you get the bridges, like literally have like a 3D clay knot and then have it split in half by like a piece of cardboard or something. I haven't made that yet, but that is my intention here, to give a better definition of what a bridge is. Let me know what you think about that. K of B, the other variable that we'll be working with in our theorem, is the length of the bridge B. So that's the number of crossings of B. So I would then show my prop again and give an example of a particular length of a bridge on that model. Mr. Kidwell, our author, he describes improper bridges, or defines improper bridges. Move these down so they match up where they were. We have three different examples or types of improper bridges. First of all, if B is a simple closed curve and your K of B, your length of your bridge is greater than 0. So we have a simple closed curve. That is our red bridge. This is our bridge here. And the number of crossings has to be greater than 0. In this case, it's 2, but we could have many more anywhere we want. we could have more happening. So as long as you have at least one crossing there, or at least one crossing under your bridge. The second type of improper bridge, if B is an open segment, okay, so we can't be closed, we need to be open, like this particular bridge. Here's our B. With one or both of the crossings at which B terminates also has B over crossing. So this, maybe it ran into something here. So this is one terminating end, but on the other terminating end, it's actually running into itself. Okay, so that's what we're looking at for this type of improper bridge. And then finally, our red again is our bridge. The crossing at which it terminates are identical. Okay, so it's like you would have had a simple closed curve, but it had an underpassing there instead. So you are running into yourself. And also the stipulation that the length of the bridge has to be greater than 1, which of course it would have to be at least 1 in order to have this type of situation occurring where it's running into itself and becoming an underpassing, but it has to be more than 1 to fit our improper bridge situation. Okay, so we have, in this case, we have 3. In order to prove Kidwell's theorem, he needs to have a lemma. If a projection of a link contains an improper bridge, then there is a projection P prime of that same link that contains a bridge B prime such that the number of crossings in the P prime projection is less than the number of crossings in the original projection, and the number of crossings in the second projection minus the length of the bridge in the second projection is less than or equal to the original number of crossings minus the original length of the bridge. Okay, so we have a few separate cases here depending on what your which type of improper bridge you are working with. So if we are working with our first type, case 1, we have the simple closed curve. If we let C, ooh, I lost my pen, I'm sorry. If we let C be any non-crossing point on the bridge, so let's say C is right here. By Reidemeister 2, in this case, we could simply move this string over. That would preserve our isotopy, and we would simply have a new projection that looked like this. And you could see that in our new projection, this would be our P of L, would be this. Our new bridge, which is our, should I color code that red? Our new bridge now has a length of 0, and the number of crossings in our, oops, that's in the wrong spot. The number of crossings in our new projection is equal to the number of crossings in the original projection minus the bridge number, the length of the bridge. In this particular example, the number of crossings in our new projection is 0. The number of crossings in our first projection was 2, and as was the number of the length of our bridge, so 2 there as well. So in this case, you can see clearly there 0 equals 0. But it wouldn't be, it's not hard to see that no matter what you had happening here, if you have the simple closed curve, whatever the bridge number is, the crossing number is going to be the same. Okay, and even if you had a more complicated one and maybe you would need to use Reidemeister 3, you're still going to end up with this same exact situation. And clearly that fits the theorem or the lemma here. because not only it's not less than, but it is the equal to part.